This is the pre-lab for experiment 18 on galvanic cells. The first step in the procedure is you're going to obtain a round piece of filter paper, and we're going to draw on it 6 circles that'll be 72 degrees apart from each other, and they'll be labeled copper, zinc, lead, silver, magnesium, and iron. And they'll be connected by dotted lines in an arrangement like this. We're then going to draw pie-shaped wedges between each of those circles, and then we're going to cut those out. And when you cut out those pie-shaped wedges, you're going to wind up having something that looks like a 6-armed snowflake, and we're going to use this to prepare our galvanic cells today. Now, to complete this, on each one of those circles, you're going to put a metal ion solution with a piece of metal on top of it. So on the arm at the very top that's labeled copper, you're going to put a copper 2 nitrate solution in that circle and put a piece of copper metal on top of that. For the arm labeled zinc, you're going to put a zinc nitrate solution in the circle and a piece of zinc metal on top of that. And you'll do that on the rest of the arm, so it winds up looking like this. This will allow us to be able to create a spontaneous oxidation reduction reaction if we take electrodes and touch them to 2 of the metals on this 6-armed snowflake. Now, in order to make a galvanic cell, we actually have to electrically connect each of the different pieces of metal. So on each of the dotted lines you've drawn, you're going to drip solution of sodium nitrate so that you make a continuum of sodium nitrate solution between each pairs of metal. This will allow ions to flow from one to the other, and we can therefore make our galvanic cells. Now, the galvanic cell is a spontaneous oxidation reduction reaction. Here's an example of a spontaneous oxidation reduction reaction that could take place on this snowflake here. The copper 2 ions that are located underneath the piece of copper metal on the top arm have a strong attraction for electrons, a much stronger attraction than the piece of silver metal way down here. But because the copper ions and the silver metal are not in contact with each other, the electrons cannot be transferred. So if we take a voltmeter with a pair of electrodes and we touch the electrodes to the piece of copper and the piece of silver, we'll cause the electrons to pass through the voltmeter, allowing the copper ions to gain the electrons from the silver metal, and we'll get the spontaneous reaction to occur. Because electrons are flowing through the voltmeter to make this happen, we have the movement of electrons, which is electricity, and our voltmeter is going to actually measure the potential difference between the copper 2 ions and the silver metal, and we can get a voltage or an electromotive force for this galvanic cell. Now, in your data table, what you're going to do is you're going to actually measure the cell potential for the piece of zinc touched to the piece of copper, the lead touched to the copper, the silver touched to the copper, the magnesium touched to the copper, and the iron touched to the copper. So that'll just be done by taking the 2 electrodes from the voltmeter and pressing them down on the 2 particular metals that are requested in part A, and you're going to record the measured voltage of each. Now, what we're going to try to do with these data here is we're going to try to calculate the reduction potentials of all 6 of the metals that are on our snowflake. Now, how do we get reduction potentials? When we talked about this in class, we found that you actually had to make up one potential, and you might recall that was the hydrogen potential for its hydrogen half reaction. We just assumed it was a value of 0. Very similar to the international date line, right? You've got to pick some place on the earth where if you travel across it, the day changes. If you don't, then time zones don't make any sense. We can't calculate any reduction potentials unless we artificially assign 1 equal to 0. And so we've decided to assign the hydrogen half reaction a voltage of 0. Well, we're not going to do that today. We're going to do it relative to copper. We're going to assign the copper half reaction a voltage of 0. So each of the cell potentials that you're able to measure in part A are going to equal the reduction potential for the reaction of the cathode plus the oxidation potential for the reaction of the anode. And the way you were putting the electrodes from the voltmeter, you were always making the copper the anode. So what we're going to do today is we're going to assign the oxidation potential of copper as 0. If we do that, then whatever the cell potential is will be the reduction potential of the metal that was paired up with the copper. And you can calculate, therefore, all of the reduction potentials for all the different metals in today's experiment. So that's going to be part A. When we go to part B, what you're going to do is you're going to measure the cell potentials for different pairs of half reactions, the lead with the zinc, the silver with the iron, the zinc with the magnesium, etc. You're going to record these. Depending upon which electrode you touch to the metal, sometimes you'll get positive voltages, sometimes you'll get negative voltages. If it's negative, you'll need to switch the electrodes so that the voltage comes out positive, and then knowing which electrode is touching which metal, you can identify the anode and the cathode from that. Now, I'm going to want you then to calculate what the reduction or what the potential for the cell would be theoretically using your data from part A, right? So you have a bunch of reduction potentials in part A. So what you're going to do is you're going to use those reduction potentials, keep the higher one as positive, reverse the lower one to make it an oxidation, and you calculate the theoretical voltage of the cell based upon your data from part A. We'll see how close it is to your measured value in the first column of part B. Then I'm going to want you to go to your textbook or to the class website and actually look up what the reduction potentials are based upon hydrogen is being assigned as value of 0. And then I want you to keep the higher one, reverse the lower one to make that the oxidation, and calculate the theoretical voltage of each of these galvanic cells based upon the book data. So here in part B, the very first column are going to be the experimentally measured voltages. The second to last column will be the theoretical voltages based upon your reduction potentials from part A. And the last column, which is highlighted right now, will be the theoretical voltages based upon the reduction potentials from our textbook. Now, all these galvanic cells we're making in part A and B are all using solutions that are 1 molar concentration, so they're all going to be standard solutions. These are all standard voltages. In part C, you're going to make one more electrochemical cell, but it's going to be a non-standard cell because the silver ion solution you're going to be using in part C is not going to be 1 molar. It's going to be different than that. So you're going to prepare another little galvanic cell. You're going to measure the voltage of this non-standard cell between silver and copper. And then I'm going to want you then to do a calculation based upon the Nernst equation and using the theoretical data for reduction potentials from your book to calculate what the voltage should be for this non-standard cell, and we'll compare and see how close we are.